Hello dear students, today we are going to start unit 4th of real analysis, and it is the last unit of your syllabus. And in this portion we study the next part of the sequence. The first topic here is limit point of a sequence. Already you have studied the limit point of this set. The similar definition is here. You know what was the definition of limit point of a set? If S is a set, then we say that P, any real number P, is the limit point of S if every open interval P minus epsilon, P plus epsilon contains infinite terms of S. Then P will be the limit point of S. This was the definition of limit point of set. Now here we are discussing the limit point of a sequence. The same definition is here. A real number P is said to be limit point of a sequence Sn if every neighborhood of P contains infinite number of terms of this sequence. The same definition is here. Or in other words, you can say P is a limit point of sequence Sn if for any epsilon greater than 0, the open interval P minus epsilon, P plus epsilon, this is the neighborhood of P, it contains infinite Sn, means Sn means terms of sequence Sn, and n for infinite value of n. It means this open interval must contains infinite number of terms of the sequence. Then this real number P will be the limit point of this sequence. Also you can write this mod of Sn minus P should be less than epsilon for infinite value of n. Then also you can say P is a limit point of sequence Sn. Now we see some example and some remarks. The remark 1, limit point of a sequence is different from the limit of a sequence. Means limit point and limit point of a sequence are different, but there is some relationship. The limit of a sequence is always a limit point of the sequence. If we have the limit of a sequence, then it will be also the limit point of a sequence, but the converse need not be true. Means every limit point cannot be the limit of the sequence. Remark 2, limit point of a sequence need not be the term of the sequence. Means it is not necessary that the limit point belongs to the sequence. Third point, if limit of Sn is L, then L is a limit point of Sn. It is discussed also in remark 1. Now we are taking some examples. Example 1, if we are taking the sequence minus 1 to the power n, then its sequence contain infinite terms, and the terms are 1 and minus 1 only, but comes infinite times in this sequence. So here 1 and minus 1 are the limit point of this sequence. Why? Because if we take 1, and neighborhood of 1 will be 1 minus epsilon, 1 plus epsilon, and you know this neighborhood contains 1 also belongs to this neighborhood, and you know 1 is infinite times in the sequence. 1 comes infinite times in the sequence, so it means this open interval contains infinite elements of S. Therefore 1 is a limit point of this sequence. Similarly, minus 1 is also the limit point of this sequence. You can check for minus 1 also. If we take this example 1 by n, simply you know the limit of this sequence is 0. So limit point will be 0. And if we want to show the limit point is 0, how to show? Let epsilon greater than 0 be given. Then by Archimedean property there exists m belongs to n such that 1 by m less than epsilon. And if we take it for all n greater than equal to m, if n greater than equal to m, then you know 1 by n is less than equal to m, and 1 by m also less than epsilon, and 1 by n also greater than 0, because n value of n is 1, 2, then 3, then 4, and you know minus epsilon is also less than 0. Exclude 1 by m from here, then you can see minus epsilon less than 0 and 0 less than 1 by n, and So you can see here, in this this is the open interval minus epsilon 2 plus epsilon, and it contains 1 by n. And what about this? This is the neighborhood of 0, because you can write here 0 minus epsilon or 0 plus epsilon. So this neighborhood contains 1 by n for all n greater than equal to m, and n greater than equal to m means infinite values of n. So it means this sequence contains infinite terms of this open interval contains infinite terms of the sequence 1 by n. Therefore here 0 is the limit point of this sequence, because neighborhood of 0, that is minus epsilon plus epsilon, contains infinite terms of the sequence. Therefore 0 is the limit point of this sequence. Now third example, if we are taking the sequence 1 2 3, this is sequence 1 2 3 4, and this has no limit point, because if we are taking a real number p and taking neighborhood of p minus epsilon, p plus epsilon, then you can see this does not contains infinite terms of this. Maximum it will contain only p if p belongs to this set, but p will be the single element, and it must contains infinite elements of the sequence to be a limit point of the sequence. Now there is one theorem, that is theorem 1. It is very simple. If L is a limit point of the range of this sequence, then L is the limit point of Sn. You know the range of sequence is the set of all distinct elements of the sequence, and it is given L is the limit point of the range of Sn. So let Sn be the range of this, then L is the it is given L is the limit point of Sn, of S. So, and you know by the definition of limit point, if L is the limit point of S, then every neighborhood of L contains infinite terms of S. And you know what are the terms of S? These terms of S are also the terms of Sn. So it means every neighborhood of L also contains infinite terms of the sequence Sn. And this is the definition of limit point. Therefore L is the limit point of sequence Sn. Now there are some notes or remarks you can say. The remark 1, the converge of the above theorem is not true. By example we can see, if limit of if sequence Sn is given where Sn is equal to 1 plus minus 1 to the power n, and you can see the limit the terms of the sequence are either 0 or 2. If n is odd it is 0, and if n is even it is 2. It means 0 and 2 are limit points of this sequence Sn. But the range set of this sequence, that is 0 2, which is a finite set, and you know finite set does not have any limit point. So we can say the converge of the above theorem is not true always. Here note 2, remark 2, that is, if all terms of a sequence are distinct, then the limit point of the sequence is equal to its range set. You know, if the terms of the sequence are distinct, then range set will be equal to the sequence, and if both are same, then you can see both have the same limit point. For example, this you can see in this sequence all terms are distinct like this, so range set will be the same, so the limit point of both will be same, that is 0. We have proved it before. Okay, thanks.